just keeping on discussing about the basics, it would be a little bit better that if I kind of get a little bit introduction on how to do those projects, and so that you can implement them easily and understand them easily. So most of the projects are simple. So you have to, the pipeline is already defined. So you just have to implement them. And I think the implementation is also there, but you just have to run it on your own, like basically change the data set and then tweak some things and then try to understand what everything is doing. I think that is how the projects are defined. I think they'll share with you when you start doing your assignments or projects. So one thing I found out after reading the projects is most of them are related to text representation. So basically, as we discussed yesterday, you have to, for any machine to understand text, you have to represent it mathematically, right? So there are different ways to do it. So if you have a sentence and you have a vector out on the right side, you have a sentence on the left side, there are different many paths to achieve that. So I'll be discussing about like what all methods are there in place, and then almost I think I'll just share my screen. Yeah. So yeah, let's open the chat also side by side. So yeah, I found out a blog, I think better than slides. This blog covers exactly what were in the list of the projects. So I think this would be better. It would be redundant to make slides, but yeah, I'll be share. You can note the link, or I'll just put the link in the chat so that you can go through it. So I think this link has everything that you need for your project, like almost. So if you can understand this blog and then understand how the text representation is going on at different levels, you would be fine. So yeah, let's skip the introduction and then we'll start with this. So as we discussed yesterday, there are different levels of text, right? In NLP. So one is corpus, and then vocabulary, and document, and word. So these are basically the terms that we will be using. So based on these, so let me just ask you. So how do you think we can achieve the mathematical representation of sentences? So any ideas? Anyone in the? So let's say I have a sentence, I have a cat. So what all possible mathematical representations can we achieve? So how do we even do that? So when I say mathematical, it's not any hidden function that just converts into numbers, right? So what is happening here? So if anybody has already used this or learned this. Any idea? Okay, fine. So not a problem. So the first thing, first, how the representations evolved is, the first one is frequency. So frequency is used also now, even now also. So it's a very simple metric to calculate the text representation. So let's say I have a cat and he has a dog. And so I have a cat and he has a dog, right? So I'll just type it out. Let's take a sentence which has repetitive words. So, and yeah, they have a car. This is fine. So when I say frequency, I'm referring to the frequency of the words in the sentence. So the frequency of I is 1, and have is 2, and a is 2, and is 1. So like that, so on. So this is the most basic representation of a, say, this is the most basic way on how you can convert sentence into numbers. So let's say you have so what we can do is we can create a like a set dictionary from this, right? So let's say, so what are all the unique words in the sentence? One is I, one is have, a, cat, car, oh, and then they, right? So there are around 9 words in the sentence, and there are 6 unique words in the sentence. So it's obvious that some of the words are repeating. So what we can do is, we can just mark out their frequencies. So I is occurring how many times? 1 time. And then have is occurring how many times? 2 times. And a is occurring 2 times. And then so on. So this is basically the frequencies. So this is called term frequency. So this is the most basic way on how you can represent any sentence mathematically. So on the first side, you have a list of words that are unique, and on the right side, you have the frequencies of them. And if you can just map the words into indexes, so let's say I'll give one index, and so I'll just have a list of words. So I'll just have a list of words and their respective frequencies. So list of words and respective frequencies, that's it. So it becomes a dictionary now. So are you all aware of a Python dictionary? So how it works? Anyone? Yes, fine. Okay. So now you have, so we can assume that now we have a dictionary. So so I'll just I'll probably type it out here. Like you can see the screen, right? Can you see my VS Code screen if I share it back? If I move the desktop? Yes. Okay, fine. Thank you. So this is the sentence that we're taking, and we are defining a dictionary here. So it's basic. So this dictionary will be very simple. So the key will be the word, and then the frequency would be the value. So I is 1, and then so have would be the word, and then key, and then the frequency of the word will be the value, and then so on. So you got an idea on how we can represent this, right? And so basically, so instead of having I, have, and the, and dog, you can also have indexes here. So let's say we already define index in so this would be 1, and this would be 2, and then the next word would be 3. So we'll have all the list of unique words, and they would be our word to index, basically. So that is just a simple representation. So that is where it all started. So to represent sentences or documents or words in math, so the first thing that we can take into account is frequency. But what do you think is wrong with this frequency? So is frequency enough to understand it? So let's just say that we have the dictionary. Oh, 1 and 2 are basically word to indexes. So how do I say this? Let me just write this so you'll get a better idea. Yeah. So see, so we have so this is basically the 1 and 2 that I was talking about. So let's say, so we have a sentence, right? And then I can have a set of the words. So which basically changes it into a unique set of words. So you know what is a set, right? So set should not have unique set. redundant values, so repetitive values. So it basically removes the repetitive values. So, and then I store them as a index list. So in the final term frequency dictionary, you can either store the word or the index. But because just for the machine, you have to give it as numbers instead of words, you'll store it as index basically. But for our understanding, we can use the words as well. So Keshava, so is your doubt clear, or is it still unclear? Okay, fine. Yeah, so I was saying, what do you think is happening with this? So, do you think the machine will be able to understand the meaning of the sentence just by saying the number of words that that the sentence is having? Would it be enough? No. So, what more can we do? So, what more is the what in? So, what else is required? What do you think? What is the key crux to the sentence that we have to teach the machine? Relation between words. Correct. Correct. The relation between words, and there is one more important thing. Semantic. Yeah, correct. Semantics is one more thing. So semantics is nothing but meaning. So we have to let the machine know both the meaning of the sentence and also the relation between the words. Just saying the frequency of the words and the number of words would not be enough, right? So if I give this dictionary to you, nobody would be able to understand anything from this, just 1122, right? So we also have to give some more information. So that is where long-term memory, long short-term memory. Okay, okay, LSTM. Oh, okay, that is a deep learning method. So yeah, correct. That is one more way in which you can encode sentences. That is correct. It's good to know that you know about LSTM. I think you are having this in your project, so it will LSTM or bird-based models you're having. That is fine. So yeah, so to include semantics and relation between words, what you can do is we can include so statistical based representation techniques. So if you use frequency or document frequency or count vectors or anything, one hot encoding or anything, so these do not involve semantics. These do not involve semantics because you're only calculating the statistics of the sentence, right? So how many times this word is occurring with this, and then how many times this word is occurring alone, and everything like that, and how many times the bigrams are occurring together. So basically, you wouldn't have any meaning in it. So in order to encode meaning, you would have to use or employ deep learning based methods, which are trained on millions of sentences, so that they'll be able to understand the context of the sentence. So until unless you are having a very huge idea on the context, you'd not be able to understand the meaning, right? So if I say a new English word today, until unless I use it in a couple of sentences before it, you would not be able to understand what's happening exactly. So so we'll be discussing about statistical methods today, and bird-based methods and Elmo embeddings and BERT embeddings. So those are something different, and you can use those to get better representation, which also involves semantics. So yeah, we'll just go with the what are the basic five, six types of statistic text-based representations that we can use in NLP for basic applications. So let's just start with one hot encoding. So one hot encoding is nothing but so let's say we have a sentence. So as you can see in the image, so the boy sat on the floor, right? So it assigns a unique hot vector to each of the word. So are you what do you think is happening here from the image? So there are 6 words in the sentence, and there are 6 vectors in this. So all of you are well known with matrices and determinants, right? So you can deal with vectors and matrices. Just anybody? Fine. Okay. Thank you, Keshav. Yeah, so this is the most basic form. So one hot encoding is the most basic thing that you can do. This is again similar to what I just did 5 minutes before. So let's say the boy sat on the floor, and I'll just run the code for you. I've just copied it. So here you can see the sentence is basically we have defined as just the boy sat on the floor. And then we are using the NLTK tokenize to tokenize the sentence into words, which gives a list of words, right? So this gives a list of words. And then what are we doing after this? So just run to make sure that you can see what's happening. So see, so first of all, what it did, it created an index. So this is what we call word to index. So word to index is nothing but a mapping of the words to indexes, so that instead of giving the words, we'll give numbers to the model. That's it. That's the only thing. So this is a word to index dictionary that we have created using the frequency by removing the repetitive words. So, and after this, what is it doing? So let's say on is, so basically the 0 is the, what is the sentence here? The boy sat on the floor. So what is the index of on? It is 3, right? Yeah. So what is happening? So you can see here. So the is in the first index. So the first index of the vector is 1. And if the boy is in the second index, the second index of the vector is 1. And so this basically is an exhaustive set of vectors that you can create, and each of the vector will have one at the position where the word is occurring in the sentence. So you can see the pattern from it, right? And this is just a abstract version of it where the indexes are juggled. So you can see it clearly here. So the boy sat on the floor. So the boy is in the second position here, and there is 1 here, and sat is in third, so there is 1 here. So these are basically 6 vectors that you can create. So this is basically the most simple representation. But what do you think is wrong with this? So so we cannot. So let's say we just have one sentence for now, right? So let's say we have to encode. So this process is called encoding, right? So converting the sentences into mathematical representations. So let's say we have to encode hundreds of documents which have hundreds of sentences. So would you be able to create sparse matrices like this, just having ones in only one place and then processing that? Would it be efficient? No, it won't be efficient. So yeah, correct. Okay, sure. Yeah, so it won't be efficient. So this is a very basic way to represent sentences, but no, as I said, nobody uses one hot encoding. It's just for understanding that. You can represent each word as a different vector. So idea that we can borrow from this one hot encoding is that each word can be represented as a vector. And so if you have another sentence, so now you can update these vectors in any way, so let's say we have another sentence, the girl sat on the floor. So if you want to create another one hot encoding vectors or any other vector representations, what would you do? You would just add a girl, right? So because the sat on the floor is already there, right? So basically you would increase this set of vectors so as to increase your representation size. So so yeah, I think that is what we can take from one hot encoding. So one thing the final thing is we can represent each word as a vector representation. Apart from this, one hot encoding is not at all efficient, and we will not use it. But this is where it started, so I am just discussing it. So the main idea is each word can be a vector representation. So let's say we have 2000 words in our vocabulary. which is filled with 100 sentences from 10 documents. So each of the 2000 words will have different vector representations, and we can use mathematical algorithms from it to calculate anything actually. So let's say, so if you understood this vector representation concept, let's say I'll just have a small question. So let's say we have two words, so king and queen. So we have derived vectors using some method. Let's say not one hot encoding, not TF-IDF, kuch bhi, like some methods. And so we have, so let's say this is 0.1, 1, 9, 10, right? So this is a 4-dimensional vector. And let's say queen is also a 4-dimensional vector, which is basically 0.1, 3, 8, 2, right? So let's say that we derived these vectors using some method, some NLP method or some mathematical frequency method, or using deep learning models also. So what operations can we do on these vectors? So let's say I want to find out how similar kings and queens are. So how similar the word king is to the queen. So what can we do here? Subtraction. Okay, fine. But a little bit more subtraction you can do, but you can do it on simple numbers, right? So if this is a vector, what exactly you can do? You're on the right path, Prasad, but so how similar are two vectors? So if I ask a question, how similar are kings and queens? The model only knows the 4-dimensional representation of both the words. And if you want to find out how similar they are, what would you do? So let's say that we have a 2-dimensional vector for now. I'll even make it simple. So I'll just say these are just coordinates. So coordinates on a 2-dimensional space, right? So kings is 1, 5, and queens is, so queen is 2, 3. What would you do now? What is the most basic thing that you can find out to establish the relation between these two? Anyone? So what exactly subtraction in terms of vectors, Prasad? I'm just asking that. I'm just waiting for the word. Okay, I'll just answer it. So it's distance. So it's the distance between the points, right? So how do you calculate distance between points? So if I have a 2-dimensional 2D representation of words, so let's say I have x1, y1 and x2, y2, how do you calculate the distance? Euclidean distance, correct, and Manhattan distance. So we can use many other distances, right? So basically it's similar. So a 2-dimensional is the most simple representation that you can do, and 4-dimensional is a little bit more complicated. So let's say you have a so understand this in such a way. So words, when represented as vectors, are just representations of meanings in vector space, where each dimension is a feature. So let's say we have features like human and gender. See, so human and gender. So let's say that if it's a human, so human will have two values, whether it's a human or not. So it will be 0 or 1. And so gender can have many values. I don't know what yeah, I'll just assume that there are many. And so let's say 3, 4 or anything. So and so on, right? So if you want to give these features to king and queens, what would the vectors be? So let's say all the vectors are represented in such a way where the first dimension is the human value and gender is the second value. So now give me the vectors of kings and queens. So gender is like, let's assume 1 is male and 2 is female for now. Anyone? So did you get my question or should I repeat it again? 1, 1, 1. Okay. So 1, 1 is what, king or queen? Correct. Correct. King. And then, so yeah, correct. And then queen would be 1, 2, right? I think you got the logic. So 1, 1 and 1, 2, if you represent in the space, they're very near, right? And then, so basically understand this like this. So if you represent the word as a vector, you are just representing them as features. That's it. So let's say you have 4 dimensions. So I'll add 2 more. Are they a good queen or good king, or bad queen or bad king? Or where did they rule? Did they rule in India or abroad? Or when did they die? When were they born? So all this information, the more information you're trying to encode as a vector, the more the dimensions become, right? So this is how you this is how basic vector representation of words work. So if you train any deep learning model like Elmo or BERT, it generates a vector representation of what, 768. So it declares 768 random variables and then updates each value in such a way that they can be represented in a 768 dimension space. And when you want to find out how similar 2 words are, you just take these 2 vectors apart and then you calculate the Euclidean distance between them, x1, y1, x1, y minus y1, and then x2, y2, x768 minus y768. So yeah, so you just calculate the Euclidean distance and you would get the distance, right? So that is how similar they are. And if you want to compare 3 words, so let's say we have kings, queens, and water bottle. Let's say bottle. So how would you represent this? So let's say 3 is for objects in gender. So is it human? No. And the gender for objects is 3. Let's say so it would be 0, 3, right? So 0, 3 is a little bit distant from 1, 2. So say king is more near to queen than bottle, right? So as humans, we know it intuitively, and by learning the language that king and queens are similar because these are humans and ruling objects, but bottle is an inanimate object, right? So that is what we are trying to do here mathematically. So all these vectors are not complicated things, but they're just representations of the words, and assume all the dimensions are features of the words. So the more features you give, the better features you give, the better representation the words will be. And the more better the representations, the better the model will perform. So basically it's understanding, right? So if you give random values in each numbers, it would not be able to identify the patterns in the words. So it has to cluster the words together. It has to identify which words are occurring together, which words are nearer together, meaningfully, semantically. So for that, it needs to understand how they are represented in the space. So yeah, this is just a digress from what we were talking, but so that is what vectorization basically means. So, and this is a very basic way to involve semantics in it using context. So we are still not saying what is the exact meaning of king, but using king in sentences where so the king is ruling the kingdom. He died in 1976. He was born in 1902, and then the king had 3 queens, and then the king was born in India. So all these sentences would have context. So all the sentences will build up the context on where the word king is used, and then that would create the feature representation, right? So the more sentences you have, the better representation you have. So this is the most basic experiment that people did with representing words along with meaning. But here today we'll discuss about statistical based representations, which would not ideally represent meaning, but because they're statistics, right? So And I think this is what you'll be doing in your project. So statistics based vector representations. So basically one hot encodings and term frequencies. We'll just go through that. And as we said, what are the disadvantages with this one hot encoding? So one hot encoding is like a highly sparse matrix, right? It just have like what negligible number of ones in the entire matrix. So you have n square number of values and you have just n ones. So that would be n to n square is very, it makes the matrix sparse, and processing this types of matrix would not be even efficient, and it would not result in such a well understood understanding of the language for the model. And yeah, this representation, as we discussed, does not capture the semantics of the word. It just captures just 1 0. It doesn't capture anything. But the idea we have to borrow from this is we can represent each word as a vector. That's it. Yeah. And what more can we do from this? So instead of representing each word as a vector and then so let's say the document has 10 sentences. So what are you doing in one hot encoding? You're using 10 different matrices which are representing this entire words in the each of the sentence, right? So, but that is, as we discussed, is highly inefficient. So little bit more optimized, what they did was where they introduced bag of words. So bag of words is nothing but you'll have a set of words. So that I think we coded it here. Yeah, so this is basically the bag of words. So even though you include more sentences to the document or your training sample, so let's say we have 5 sentences. So so let's say there are 2 only here, as I discussed. John is happy, is not hungry for apples, and Mary is hungry for apples. So what are they doing here? They're calculating the set of the words which are basically occurring in the all the sentences combined, and then they are assigning the frequencies to it. So how many times the word is this word is occurring in the entire set of documents, right? So yeah. So how do we do that? We just use a count vectorizer for it. So count vectorizer is an inbuilt. It just gives the count of the number of words. So it first divides the words, the set of sentences into words, and then makes a set out of it to remove the redundant words, and then gives you the frequency of the words. So yeah, this will be the same output, but if you want, I'll just run it. Count vectorizer. Yeah. So what was the sentence? So I have a cat, I have a dog too, my friend has a car. So basically have is occurring 2 times, I is occurring 2 times, A is occurring 3 times. So we can see, so what they do is we'll just append all the sentences together, and then we'll calculate the unique set of words that are occurring, which will be our dictionary. So this is called vocabulary. So this is one important term in NLP. Was vocabulary is nothing but the entire set of unique words that you're using in your training sample. So if you say you have 100 sentences, you list out all the words in the 100 sentences that are occurring, and that will be your vocabulary. It's a set. So it does not have redundant words. It's basically a dictionary or a set, or it's just a list of words that are occurring, unique list of words. So that is vocabulary. It's just simple. And okay. Yeah, what are we doing here? So we are getting a similar type of list, which basically gives what are the frequencies of the words in each of the documents. So here it's considered as one document because it's one sentence, but in my case it was 3 sentences, so it's considered as 3 documents. So if you merge them together, what would you have is you would have a single set of words which along with their frequencies. So that is your basically the term frequency, nothing left, nothing more. And what are the advantages of count vectorizer? It's so it's easy to implement. It's just counting the frequency and then storing them as a dictionary, and we get the frequency of each word, and the size of the vector is the size of the dictionary, right? So no matter the number of words in the sentence, we always have the vector size equal to the size of the dictionary. But what is the disadvantage of this? What can be the disadvantage of this? So consider the size of the dictionary. What can be the disadvantage related to the size of the dictionary? So if you're, let's say we have 10 sentences and we are having all the vectors in the size of the dictionary. So let's say 10 sentences which have 150 words, right? So if our 10 sentences have 150 words and you're representing each of the word or each of the sentence in 150 dimensions, wouldn't it be too much for a statistics based method? Wouldn't it be too much? Because, so let's say we are training this on 10,000 documents or 1 billion word tokens. So how will your vocabulary be? Your vocabulary will be the entire English dictionary. And that would not be much efficient, right? So storing the entire dictionary and then processing through it again and again just to get the frequencies and everything. So that is one negative point with representing dimensions with the size of the dictionary. And this also, as we said, does not extract any semantic meaning from the words. And it also does not it also does not store any positional information of the word. So it is independent. So all these that we did till now are independent word representations. So we'll take out the word specifically and then count how many times it's occurring and then store it there. So that will be our vector. And so that does not take into account what word is occurring beside it, how many words apart is it occurring from this word. So no positional information from the sentence is encoded. So, but as we intuitively know, positional information from each sentence is very important, right? So let's say I have a so what could be the issue with this? So I'll just note it out. So let's say I have a sentence called I have a dog. I think I'm using the same sentences again and again. Let's say something. I can swim. And then swim can I. Right? So these are very simple sentences, but let's say we have a little bit more like 10 word sentences or 20 word sentences where if you juggle the order, if you don't store the positional information of the word, wouldn't so aren't we giving the model random information? So until unless we give the context and the syntax of the language, if there are no rules that it can define, it would just be it's just like confusing the model. So we cannot just give randomly formed sentences and then expect it to understand the entire language, right? So that is why positional information is also correct. So in this case, we are not encoding any positional information. We're just saying swim is occurring one time, can is occurring one time, and I is occurring one time. But actually swim can I doesn't make sense. So if I ask the model to predict something and it gives me swim can I, just because it saw the sentence before, it saw the frequencies before, it doesn't make sense, right? It's not a very good chatbot or it's not a very good NLP model. So one more thing that we can do is to represent positional information. So yeah, that is one of the disadvantage. And correct. So we'll go to TF-IDF. So has anybody heard of TF-IDF representation before? TF-IDF calculation or frequency? Any idea? Okay, fine. So I'll just go ahead. So TF-IDF is nothing. So nothing but a little bit more advanced representation of the term frequency. So what we do here is TF in TF-IDF is the term frequency, and IDF in TF-IDF is the inverse document frequency. So instead of just saying that this term is occurring these many times, we'll also say that this term is occurring in these many documents. That is basically the most intuitive thing that you can understand from this. So it's occurring these many times and these many documents. So a little bit more information that we are trying to encode. So the mathematical way to do it is okay, fine. So TF of a term comma document is nothing but count of term in dictionary by number of words in the dictionary, right? So not dictionary, sorry, document. So document is very commonly referred here, but let's not confuse between document and sentences. Document can also be a sentence. So they just broadened it up, and everybody in blogs and NLP use document to term that, but it's basically a sentence. It's nothing more. It can be also a set of sentences. That's why they just termed as a document. So count of term in document is basically you'll get the each terms. So you'll have all the set of terms, right? You create using a set that we have just seen before. And then you count all the number of times that each word is occurring in the document. So that will be a term frequency, very simple. And what will you do after that? So using so inverse, they also define another term called inverse document frequency. So it's nothing but log of the ratio of number of documents to the number of documents with the term in them. So let's take so it's basically log of, let's type it out, number of documents by number of documents with T. This is basically the IDF. It's inverse document frequency. So you understood, right? What they are trying to intuitively do here. So they're trying to find out how many documents have the word T. So they're also trying to include that information. So let's say that this term is occurring only in this document. So we should not give this much more importance. It's not much more important to the entire corpus. So that is what they're trying to do. So they're trying to increase the context of the word. So they're trying to basically encode the context of the word also. So let's say we have 10 documents and one word occurs in all 5 times each, and one word occurs in only one document, but for 10 times. So which word do you think, word number 1 or word number 2 should be having more importance while encoding the, so should we give equal importance to them? Because the number of times the second word is occurring is 10. If we just take term frequency, it would be the second word number 2 would have more importance, right? But would we want that in all the cases? Nobody. Okay, fine. So we wouldn't want that in all the cases, right? So because all the words occurring in, so the number of so let's say word 1 is occurring 5 times each, each document. So we have to give more importance to that because it's occurring in more documents and it has more context. So we should give more importance to that word. So that is where the mathematical way of representing that came in. So it's basically TF-IDF, and you just multiply these two values now to get your TF-IDF score. And that's it. And I think this is you can just try this code out, TF-IDF. I'll share the link and it would work. And yeah, so what are the advantages here? It's easy to understand and interpret, and it also penalizes both high and low frequency words, right? So it's just like if the word is and a and then Taj Mahal, so these are occurring very in like so there are stop words, right? So stop words, is, a, the, and everything. So these all words are occurring too many times in the document, and we wouldn't want to encode all this information much, right? So we don't need to give much importance to this. Like these are just helping words for us to understand the syntax, but the actual meaning is actually embedded in some other words, not these, right? So that is where it comes in. So this would penalize the log factor of the TF-IDF would penalize the term frequency in such a way so that the TF-IDF score is reduced, and this would be given much less importance. And the words which are occurring even in low frequency, like only 1 time or like only 2 times in like document of say 100 pages, so we would not also give importance to that. So it's basically improving the representation. So you're given a text and you have to represent it mathematically. How optimized you can go? So what more can you do to represent it better and let the machine understand, know better, and but also at the same time take care of space complexity, time complexity, and then the if there is a GPU processing, like, so basically all these factors will come into account while developing representation techniques. And so, but deep learning has thrown all these aside because they also involve semantics, and that is a way better representation, and they would give accurate results than this. So for statistics, the thing is we need more and more data. So just using a couple of sentences like we are doing now wouldn't make any, doesn't make any change. So we have to have like lakhs of sentences, tens of lakhs of sentences, and then we need to extract statistics from that in order to develop at least a reasonable amount of, reasonable quality representation from text. But from using context and meaning, even if you see let's say 1,000, 2,000 sentences, it would be enough for the model to understand the context, right? So that is where deep learning models are way ahead in terms of text representation when compared to statistics models. Yeah. And as we are discussing about context, right? And one more thing, the disadvantages of this is it's again not considering the semantic meaning, and it's not considering the positional information of the word. So both of them are still not done. So still not solved, both of the questions. And so we were discussing about context, right? So what do you think? What is context? So just what thought do you get when I say context? Anyone? Any idea, anyone? What do you think is context? Okay, I'll just say. So context is nothing but the premise or the discourse. So we are talking in the context of NLP, and you are studying college. So this is all in the context of academics. So that is basically context. So so let's say we have the word cool, right? So as we can see in the left side. So cool. Cool has different meanings based on context. So let's say you are cool, he is cool, she is cool, and then the wind is cool, the room is cool, the weather is cool, so the bottle is cool. So all these have different meanings. So based on context, so what noun is using this verb cool decides what cool is, right? So this is all context. So you need to understand the most basic thing while doing statistics based representation learning is you also have to encode context. Just encoding the individual words would not be much efficient at a large scale, because the word cool might have multiple multiple meanings, and they would all be confused. So the model would be confused if you are saying so statistically. So if it has different meanings and we are trying to encode them all together, it would just confuse among all of them and it would not provide accurate results, right? So what is the next thing that people discovered? It's n-grams. So n-grams are nothing but sets of words. So it's basically like clusters of words. So instead of saying, so let's say I have a CAD NL, so not CAD word sentence, NLP has changed the word. So what are the n-grams? And so n is basically the size of your cluster. N is equal to the size of your cluster. So let's just define it as a cluster for now. So let's say 2 grams, right? Let's take example of 2 grams, which are also called bigrams. So what are the 2 grams in the sentence? NLP has changed the word. NLP has changed the word, right? So do you understand what bigrams are? So these are just 2 words taken at a time, 2 consecutive clusters of 2 words taken at a time. So yeah, okay, thank you. So these are basically 2 grams, and if you want to find out 3 grams, what would you do? Which are also called trigrams. You would just cluster 3 words together instead of 2. So NLP has changed the correct term here, trigrams. So NLP has changed the and changed the word. So these are trigrams. So do you understand what are we trying to do here, or what pipeline is trying to do here, or what the n-gram representation is trying to do here. So why are we doing this? Any idea? Why do you represent clusters? You have the words, right? Simple enough. Why are we even bothering to do this? You can just say NLP has changed the world and then get vectors for all of them, and it would be fine, right? Why are we doing this? Fine. The reason we are doing this is to encode the context, as we discussed. So context is the important thing. So NLP has changed the world. So let's say we have a sentence called I am cool, and another sentence called the bottle is cool. So if you encode this sentence into these two sentences into trigrams, so what would you have? You would have an I am cool as one of the trigrams in the entire list, and then bottle is cool, right? So we can see that cool is occurring in both of the contexts, and both of these are different meanings. And so these should be represented in a different way. So, but if you use a single 1 gram, so if you use a unigrams, these are called unigrams. Whatever we were discussing till now are basically unigrams. It's just basically one word, one cluster of word, cluster of size 1. So what would you do? You will have two cools which have the same representation, and then the model will be confused on what to use. But here it's you have a I am cool and bottle is cool, right? And what more are you doing here? You're also encoding that I is occurring after am. Am is occurring before cool. So here this is the first step where you try to represent the positional information little bit. So this is the first idea to represent the positional information, so n-grams. So it is not exactly a relative positional information in relative to the sentence, but these are just context-based position representations. So not exactly positional representations, but little bit head start, I would say. So this is where and then you do the same thing, or you do the same term frequency and then TF, IDF and everything, but the terms are now bigrams, not unigrams. So these will become so I am cool and bottle is cool would become your I am cool and the bottle is cool. So instead of having 5 different words, you'll have 3 different trigrams. So these will be now used to calculate your TF, IDF score, or term frequency, or whatever. And so this would be a better representation than unigrams, right? So it's trying to encode both the positional information and the context. Correct. Yeah, and so yeah, as we discussed, it's trying to encode the context, right? So it's trying to encode the meaning also. So let's say these two sentences have I am cool and bottle is cool have two different meanings of cool. And when I say that in one case cool is occurring with the word I, and in the second case it's occurring with the word bottle, and now these both are different, so these both will be encoded differently. So basically it's two different, we are trying to establish two different meanings to the word, right? So it's basically another head start into representing meaning also. So meaning and positional information we can do using this n-grams, right? And yeah, and what are the more advantages? It's easy to implement. It's just calculating the sets, and you can just so how can you do this? You can just have a for loop through the sentence. The most basic way, you can optimize that obviously, and most basic way is to have a window, and then you move that window, and then take all the words in that window, and then store them as tokens in your set or dictionary or whatever you want. Yeah, and what are the disadvantages in this? It's basically we cannot capture the relationships between the words or semantic, like it's we can do a little bit so we can assume that it's capturing a little bit of meaning through context, but it's not exactly capturing the entire meaning, right? So we need to have a much more complicated representation in order to encode the meaning also. And out of vocabulary words, so basically we discussed what is vocabulary, right? Vocabulary is nothing but the entire unique set of words that are in our training sample. And what do you think is out of vocabulary? So let's say our model is trained on only animal names. Let's assume that. So it's trained on dogs, cats, peacocks, and then fox, and then tiger, and all the animal names in the world. And then you give a random name called book, and then it will not be able to understand what's a book. And so it's basically your it reached an impasse. So it's basically you wouldn't understand, the model would not understand what a book is, because you have not, the book is not at all in the training sample. So these types of words are called out of vocabulary, right? So if the words are out of vocabulary, the model would not be able to identify anything. It will just throw an error. So in terms, when we were dealing with unigrams, this out of vocabulary has never happened, right? Because we were always dealing with the entire set of vocabulary. So we are representing all the words in the size of vocabulary. So we always have the vocabulary with us. But when you have bigrams or trigrams, the same bigram, it's possible that you would have a different bigram, right? So let's say we have let's assume the same case. I am cool, the bottle is, and bottle is cool. So these all have words what I am cool bottle, right? So let's say we have another trigram, which is cool, another bigram, let's say cool bottle. Cool bottle is, right? So this trigram is very new to the model now. So it knows that it has seen cool and bottle and is, but it hasn't seen cool bottle is. So the disadvantage with this is we cannot cover all the permutations of the words. So it's very difficult to cover. And if you say, so the vocabulary of English language is itself very complex. And if you want to say, if you want to select 3 words out of this vocabulary and then calculate all possible permutations, it will be very little, like very much more mathematically complicated, right? So that is one of the disadvantage. And so yeah, I think and text classification we can discuss, and actually it is one of your project to classify. I think it was what was it? I think it was sentiment analysis, I guess. So do you already know your projects, or am I revealing this too early? I don't know. So anyone, do you already have your projects in place, and do you know what you will be doing, and did they give you like any list or anything? Oh yes, okay, fine. Oh, were these the same? Because that's what they give me. So it has one bird-based representation learning, and then topic modeling, and one sentiment analysis, I guess. If you have seen Krishna like this, like, are they the same? One spam, yeah, okay, yeah, spam, correct. Spam classification, and then sentiment, and then topic modeling. Okay, I think we're in the same path, yeah. Yeah, okay, so okay, so fine. So all these projects are using these. So basically, as I said, so once you have vector representations of all the words, you can do any sort of mathematical, juggling with it. So if you want to find out how similar two words are, you can find out the distance between them. If you want to cluster the words, you can just map them on the graph and then see how which words are together. There are obviously clustering algorithms for that, but for intuitive sake, I'm saying this. And if you want to say classify a word. So if you want to say classify a sentence, so what would you do? So let's say you have a list of sentences, right? So let's say you have sentences list. So you have a sentences list, and then so it's already labeled that these sentences are. So let's just discuss the example case of your project only. So it's basically to classify each of the sentence into whether it's a spam or not, right? So what would you do? So it's a labeled data of sentences, list of sentences, spam or not, right? So you have this. So you have 100 sentences. saying that whether they're spam or not. So what would you do now? You have the list of sentences. You would get some kind of vector representation for it. Let's say it's TF-IDF if it's most complicated till now. And then so you now as you have a list of vector representations, so what the next step is to get the list of vector representations for all the sentences. So now as you got all the list of vectors, now we just became mathematics. So now we forget about language. The thing that we can do in language that we already did by using TF-IDF, right? And what will you do now? We'll have all the vectors together, and so basically the input of the function is the vector, and then the output would be the label, right? So we are basically training a classifier. So in this case, I think they asked you to train a random forest, and so basically you would train your classifier on these vector representations, and then so to predict whether the given sentence is a spam or not. So what would be the proportional thing here? So the better the representations you develop, the better your classifier would work, right? So when you're doing this, so the one thing you have to also remember is what more can we do to increase the quality of the representation. So as I said, you need to remove stop words. So these are basic pre-processing steps that we can take into account while doing this, calculating these vectors, so that it would help the model to clean out the junk in the sentences. So removing stop words, and then removing any like punctuations, or like cleaning the text, basically I would say cleaning text, and then removing spaces and everything, and then you will have a final set of important words left in the sentence, and then you would use those to get your vector representations, and then train those using a classifier, and then that will detect whether it's a spam or not. So that is one of your projects. So all of your projects are basically the same thing. The basic layout is the same. So the first step is to get representation. So basically, I'll just even go a little bit more behind. So first step is to get pre-process the text. So this entire thing is called pre-processing. We can call it that. And then what do we do after pre-processing the text? We get the representations using any of the methods that we just learned, or it might be a deep learning method also using Elmo or BERT. So there are pre-trained models, right? So which also give vector representations like fast text or glove. I'll just add those names here. So after you get the representation, what do? We perform the task, which can be classification or regression or distance or anything, clustering. So basically, so the spam project is based on classification, and topic modeling would be semi-supervised. So it would involve a little bit of clustering, and so basically it's the same layout. So first you pre-process the text, and then get the representation using any of the methods that we just discussed, and then perform the task that they're asking for, right? So it's that simple. And yeah, and okay. So you can refer to this random forest. So I think it would be given as you will be given a code anyways, and then you have to perform the like you have to run the code on your own data set, and then try to tweak some things and understand basically. I think they have explanations and everything also already well defined. And I've seen the projects. I don't know whether you have, or I don't know whether you have just the names or anything. So it's the same thing that we're doing. So we are loading the data, and then what we are doing the pre-processing of the text, and then what are we doing? We are and then they are using TF-IDF to calculate the vector representations, and then they're running the classifier to get the accuracy, and they're surprisingly getting 0.78, which is very good. And I mean, for a statistics-based low data classifier, it's very good. If you train it on like 10, 20 samples, it would obviously not perform very well. But if you have like hundreds and hundreds of samples, thousands, so it would do good. And yeah. So yeah, that's all I wanted to cover today, because this blog has very good, it added up everything that the projects needed, and that's why I used this. And one more thing is fast text and glove, and then so these are pre-trained embeddings which are already in place, and you can just play with them in Python if you're curious enough. So this basically give you like 300 or 400 dimension vectors, and then you can so I think you would so if anybody is still having any doubt in why we are representing them into vectors, you can just do the simple task of semantic similarity. So semantic similarity is nothing but calculating how similar two words are based on meaning, right? So it's semantic similarity. So how similar are the semantics of the words? So how you can do this? You can get representations using fast text or glove, as I said, and then get those vectors, and then write your function to calculate the Euclidean distance between them, and then they would basically give you how near they are, right? So you would understand what's exactly happening here. So vector represent a text representation is the most basic thing in NLP, and we have everyone has to do this in some sort of the way, like statistics, deep learning, or anything, in order to let the machine understand what's happening, right? So this is the main process. So this is where we are converting words into maths. So how good you do this represents or relates how good your model will perform. So many more tweaks, and then many more steps are done at the same time while pre-processing and then while calculating the vectors to increase the accuracy. So all those you can explore, I think. And yeah, I think the session will be done for today. If you have any doubts, just please let me know in the chat. Anyone? So anyone has any doubts or anything? Did you understand why we are representing, why we are doing this, and what more can we do after we get the mathematical vectors? And any doubt in anything? Like, just let me know in the chat. I'll be there. And if you have no doubts, I think you can leave the meeting. It's fine. Yeah, thank you, Prasad. Okay, thank you everyone. As there are no doubts, I think we'll stop the meeting.